Okay, let's talk about conditional probability. And before we get into it, let me just sometimes say that conditional probability is one of the more difficult concepts in probability to learn and more importantly to learn how to calculate these probabilities. So just this is maybe one of those videos, and luckily it's short, where you may want to listen to it a couple times to actually figure out how we calculate conditional probabilities. All right, so let's start with the definition. So what is a conditional probability? It's the probability of an event occurring given another event has already occurred. Okay, so something has happened and we're interested in the probability of the next event happening. Okay, and keep in mind what this is the probability of the second event in a sequence of events. So it is not the probability of the sequence of events, but rather just the probability of the second event after something has already happened. All right, in probability speak, it's this capital P, and we see this capital A with a vertical line, capital B. And the way that is read is the probability of event A given event B has occurred. All right, so again, that vertical line that you see is read as the word given. All right, and so we are trying to find the probability of A knowing event B has already happened. All right, so let's go through a couple of classical conditional probability examples. So two cards are selected in sequence from a standard deck. Find the probability the second card is a queen given that the first card is a king with no replacement, meaning you've got a king in your hand, I deal you a card, what's the probability that second card is a queen? Okay, and so let's take a look at how to answer this. So that numerator is going to be the number of queens given a king has been removed, divided by the total number of cards given a king has been removed. So how many queens are in the deck if you have a king in your hand? And the answer there is that we still have 4 queens in the deck. All right, let's think about the denominator. Total number of cards given you have a king in your hand. Well, if you have a king in your hand, 1 card's been removed, so now there are only 51 cards in the deck. And that's how we get our probability of 4 over 51. Let's consider another example. 2 cards are selected in sequence from a standard deck. Find the probability. The second card is a heart, given that the first card is a heart. Okay, so again, let's think about how this breaks down. That numerator is going to be the number of hearts, given a heart has been removed, divided by the total number of cards, given a heart has been removed. So we know that in total there's 13 hearts, but you have 1 in your hand. So how many hearts remain? 12, like we see in the numerator. Okay, again, you have a heart in your hand. How many cards remain in the deck? And that's 51. Okay, so we get our answer of 12 over 51. Okay, so let's think about an empirical conditional probability example. And before I get into this, what you're seeing there in the middle of the screen is what's called a contingency table. So it's kind of a 2-factor table, and here what we're looking at is a child's IQ and whether or not the child has a specific gene. All right, and just FYI, I love to test with and quiz with contingency tables because it's so easy, I think, once you practice them to come up with the different probabilities. Okay, so let's take a look at this first example. Find the probability that a child has a high IQ given that the child has the gene. Okay, so my first question to you would be, what has happened? What has occurred? And the answer is what follows the word given. So what has happened is the child has the gene. Okay, and that is why I have colored the gene column pink, because we're stuck there. We know the gene is present. So now we're going to use only this column to calculate our conditional probability that the child has a high IQ. All right, so of the kids that have a gene, how many have a high IQ? And the answer there is you see 33 have the high IQ and the gene. How many kids have the gene? And you see 72 as the number with the gene. Okay, so again, that numerator is the number with high IQ and the gene. Okay, and at this point, we see that overlap there as 33. And then we're restricted in the denominator to only the number with the gene because the gene has occurred. The child standing next to us has the gene. All right, let's find another probability. Let's take a step back and go back to last lecture and use this table to simply find the probability that a child has a high IQ. All right, well, what would be the probability the child has a high IQ? Well, that numerator would be the number with a high IQ, and the denominator would simply be the total number in the sample. And so we see the number with the high IQ is 52, which is the subtotal of high IQ, all right, divided by the total number in the sample, which is 102. All right, find the probability that a child does not have the gene, given that the child has normal IQ. Okay, so again here, what follows given, and that is that the child has a normal IQ. This has happened. So again, now we have a child next to us. What do we know about this child? It has a normal IQ. And so that is why I have shaded the row of normal IQ pink, because we are stuck on this row. We have to calculate our probability from this row only. Okay, so how many kids on that row do not have the gene? The answer is 11. How many kids total with normal IQ? That answer is 50. All right, so again, number with no I gene and normal IQ is 11. The number with normal IQ is 50. All right, so there's two types of events we want to talk about, okay? And they are called independent and dependent, okay? So every set of events will either be independent or dependent. And I think it's easier to approach this by defining independent, okay? And so independent means the occurrence of one event does not affect the probability of occurrence of another event, okay? And the way we think about that in terms of probability is to say that the conditional probability on A is simply equal to the probability of B, okay? And so we see that there with the probability of B given A is simply equal to the probability of A. In other words, conditioning on A does not change the probability of B, okay? What about dependent? Well, maybe I'm being silly here, but dependent is simply not independent. So in other words, that equation we see under independent is simply not an equation now. In other words, conditioning on A does change the probability of B, okay? So again, conditioning on A does change the probability of B. So if we want to, if we're given, say, a classical example and we want to solve as to whether or not these two events are independent or dependent, we need to solve for both of these entities. We want to solve for the probability of B given A, and we want to solve for the probability of B, and we want to try to see, are these two fractions equal to each other or not equal, okay? So let's take a look at an example. All right, so selecting a king from a deck of cards A, not replacing it, and then selecting a queen from the deck, okay? So the probability of selecting a queen, given that you have a king in your hand, we know this, we just calculated it, right? We calculated it all the way back here, all right? So we know that that is 4 over 51. The conditional probability is 4 over 51. All right, what is the probability of simply selecting a queen? Well, there's still 4 queens in the deck, but now there's no card in your hand. There's 52 cards in the deck. And so the question is, Does 4 over 51 equal 4 over 52? And the answer is clearly they are not equal. So in this situation, these two events are dependent. Okay, let me give you a hint to carry forward, especially when it comes to time for the exam. Anytime you are not replacing something, they are going to be dependent events. Okay, so if we've got a drawer with 12 socks in it, what's the probability that the second pair is white given the first pair is blue, and you don't replace the blue pair? Those are dependent. Okay, so again, when you see that terminology, no replacement or not replacing, I want you to think dependent. All right, let's look at this second example. Tossing a coin and getting a head, and then rolling a six-sided die and getting a 6. Okay, well, the probability of getting a 6, given we flipped a coin and got heads, is 1 over 6. Right? There's 1 6 on the die, there's 6 sides to the die. All right? But isn't this just simply the probability of rolling a die and getting a 6? And it is, we see that, of course. In other words, this may be hurting your head a little bit to think about because this example is so trivial. But look at it this way. When has tossing a coin ever influenced the probability of some number you would get on a die? And the answer is never. Tossing a coin and rolling a die are independent events. They don't affect one another, okay? So again, since the probabilities are equal, they are independent. But I think also what I'm hoping is that as I went through this, you are asking yourself, well, aren't they going to be independent because coins and dice don't affect each other? All right, let's think about a couple other examples. And these are ones where they're more subjective. We don't calculate them, but there's certainly something like this I could ask on the quiz or on the exam of, hey, what do you think? Is this independent or dependent? So driving over 85 miles per hour and then getting in a car accident. All right, well, clearly this is going to be dependent because we know that speed contributes to accidents. So the faster you go, the likelihood of getting in a car accident increases. Okay. Second example, exercising frequently and having a 4.0 GPA. All right, and here's an example of independent. All right, because exercising is not going to change the grades you get. And I really say this to all the girls out there listening. We have this incredible tendency of overthinking everything. And don't overthink this. Don't sit there and go, well, they say if you exercise, you have more energy to study. Nope, don't do it, okay? Do not let your brain go down that rabbit hole. Exercising does not change grades. Independent.